Okay, we're now continuing with the problem sets about buffers. And in this series of questions, we're going to look at how buffers are actually prepared. Of course, you already know that the easiest way or the logical way of preparing a buffer is simply to mix the weak acid and its conjugate base in certain amount to give you the pH of the buffer that you need. Another way to get it is actually mixing and reacting a weak acid with limited amount of OH- such that the OH- gets neutralized in solution and gets converts some of the HA into A-, such that you end up getting the weak acid and its conjugate in solution. As well, I could also, it's not written here and we don't have an example of it, but I could also have a base reacting with an acid. So an A-, let's say, reacting with an H3O+, and that can give you HA in solution. And we may see some of that in at least in titrations. Okay, so we also have an ampholyte, which is almost like a base. Or an acid, again. In this case, it's considered more of an acid. As I'm reacting it with OH-, it gets deprotonated. And so we get A2- in solution. This A2- in solution and HA- form a couple of buffer type. Of course, I could also take this ampholyte and react it with H3O+. Then I end up getting, again in limited amounts, I end up getting H2A and HA-, which is another couple, which will give you also a buffer, but of course at a different pH. At the end of the course, after titrations, I will do question number 30, which is a triprotic acid with OH-. And that can end up giving me up to 3 different types of buffer solutions, because we're going to look at the buffer domains, and we're going to do that after titration along with question number 10 in this course. And in this as well, I'm going to look at question number 44, which is a generality question about buffers. So again, these are just some examples of how to prepare a buffer. And in the course and then PDF of my course, there is some theory about it. But the theory, you know, once you apply it as an example, you get that theory. So we're just going to apply the examples. Number 36. If I have a 0.1 mole of formic acid and X mole of sodium formate, again, always the base A- always has a cation beside it, and it comes in the form of a salt. Just remove the salt, Na, or the cation, and it ends up becoming the A-. So indeed here, what type of question is this? I have the acid and they're asking me how much base, conjugate base, should I add to a 1 liter solution of water to get a pH equal 3.74. So what do you have? You have the pH of your buffer type system, and you have to put in your mind that this is indeed a buffer because I have an acid and its conjugate base. So I have to find out how much base should I add into this to get this pH. Now I changed this number slightly. In your book, in the TD, it's 3.74, okay? In your exercise book, it's actually 3.75, but I thought it might be better to change it slightly differently from the pKa. If indeed it was the pKa, automatically you're gonna see in a moment what I have. So again, you have to recognize that you have a buffer type system because you have an acid and its conjugate base, and therefore buffer, use Henderson, automatic, Henderson. When I have Henderson, pH equals pKa plus log of the bases divided by acids, if I now have the pH of my buffer, I put it in. Of course, you can get pKa. If they give you Ka, get the pKa. Here you have the pKa. So I have pH, I have pKa. What does it automatically tell me? If I have both of those, I can easily calculate the ratio of A minus divided by HA. And if I already have any one of these, like here, I have the concentration of HA, which is 0.1 mole divided by 1 liter, which is also 0.1. Great. Now look at me here. I changed this number. It was 3.75, but if this is 3.75, there's pointless to do a calculation because automatically A minus should equal to HA because the pH of the buffer is equal to my pKa when the A minus equals to HA. So I changed that slightly. If it's a bit different, calculate the A minus, and my A minus will be 0.97 mole per liter, and I have a 1 liter solution. So if I want moles, it's 0.97 moles. Again, here you could actually put moles divided by moles. You don't have to put a concentration term. You can just put moles. Clear? Okay. Next, part B of this question, they said, if I add 500 milliliters of water, what happens to the pH? From now, guys, and always, a buffer solution is not affected by the volume of that solution, okay? And I'm going to prove it to you that it's not affected. So if it's not affected by dilution or volume, let's see why it's not. The new volume that I had before, it was 1 liter. If I add to that 500 milliliters, now I have a new volume, which is 1.5 liters. Use Henderson, right? Because we have a buffer, we use Henderson. Again, remember the moles that I had calculated, 0.97, and it was 0.1 moles of the acid divided, the base divided by the acid. If this volume was 1 liter before, or if it became 1.5 liters total volume, still, look, the total volumes cancel off. So no matter what the volume is, my pH remains the same, okay? So the pH is still 3.74, even if I add 500 milliliters of water, even if I add 1,000 milliliters of water, okay? No change in pH when I do a dilution for buffers. Though, again, the buffer can be affected by the concentration of A minus and the concentration of HA due to their change in the number of moles. Now, if you change the number of moles, you will get a slight difference in the pH value. Number 45. Again, now we're preparing, again, this is a type of system where we're preparing a buffer by adding an acid and a certain amount of its base. We have the Ka given, and this is an MCQ question, and we also have a molar mass. In this case, they want, consider a 500 milliliter of nitrous acid. They gave us the concentration. Calculate the mass of the salt of the nitrate, sodium nitrate, required to obtain a buffer of pH 4. So again, in these types of questions, I have the buffer pH. It's already given. And I have, let's say, I may or may not have the concentration of 1 acid in solution. So again, we start with Henderson. We have the buffer pH, so put that in. You have the pKa, or if you don't, get it from the Ka value, minus log of the Ka, plus log of the concentration of the base, NO2 minus, divided by the concentration of the acid, HNO2. And again, I don't need to put volume here. I already have a concentration 0.5, so that's enough. You don't have to multiply that by 500 and then divide by 500, okay? You don't need that. You already have a concentration. So find the concentration of NO2 that you need to make up this type of buffer. What you have to do is, again, this is mathematics, 4 minus 3.34, take the antilog, so 10 to that value, multiply by 0.5, you get the NO2 minus. Now find the number of moles, the mass of NO2. How do I get the mass of NO2? Well, I have the concentration of sodium, nitrate. I have the concentration of the nitrite. I can easily get the number of moles. That's concentration times volume. Concentration times the volume. Now you need the volume in liters because you want the number of moles. So you would multiply this concentration by volume, get the number of moles of the NO2. And of course, the number of moles of NO2 minus is equal to the number of moles of sodium NO2 because it's a 1-to-1 ratio. Now, if I want the mass of the sodium NO2, mass is number of moles times the molar mass. So take the number of moles of the sodium NO2, multiply that by the molar mass of the sodium NO2, sodium nitrate. Then you get the mass of it. Okay? And so if you look at the mass, the answer is E. Well, the closest answer is E. Okay, so here's again, we're going to 45. What I did here is, if I take the pKa, a slight modification of this number, like if this was 3.4, it makes a big difference if it's 3.34 and 3.35. And just to get to the closest number, and so that my answer is E, I switched the pKa value to 3.35 and carried everything through. I also carried all the digits to get to the closest answer. Nonetheless, none of the answers, if you look at them, are close to 77 or 78. So if you get something like 78 or 77, don't worry about it. All is correct. Okay. So choose the closest answer. With these things, a small variation can make a difference. Okay. Number 39. Okay, again, we're still preparing now a buffer by mixing an acid and its base in certain amounts, okay? Consider two solutions, an S1, which is ammonia, and an S2, which is ammonium chloride. Again, ammonium chloride is a salt, remove the Cl, so ammonium. So I have two separate solutions. They have the same concentration. They're asking, calculate the volumes of V1 of ammonia and V2 of the ammonium that we need from solution 1 and 2 in order to prepare a 1 liter solution having a pH of 9.6. Of course, they don't tell you that this is a buffer, okay? Well, okay, but you have to know that the minute I mix ammonia with ammonium, that this type of solution is a buffer. Okay. And once you know that, you're making a 1 liter of a buffer and you have the pH of the buffer that you're making. So what do you use? Henderson, exactly. With the concentration of the base divided by concentration of the acid in the buffer. You have the pH 9.6. You have the pKa given 9.2. So what can you find? Of course, the ratio of the base to the acid. You can go ahead and find that ratio. And since I have the concentration, I could go ahead and actually do more here. I'm going to put log. Remember, here I have concentration times volume 1, how much of this buffer I need, divided by total volume, which is 1 liter of my solution. And the concentration of A is 0.1 times the volume of A divided by the 1 liter. So here I just, calculated, if you will, the number of moles such that I can include a volume term in that. Clear? Okay, so you're going to take the 9.6 minus 9.2 and then 10 to the power of that number, and then you get the ratios. And because these concentrations cancel off, you get now a nice ratio. And if they don't cancel off, you get a number. So you still get a number here, which overall you're going to get a ratio between the two volumes. Try this by hand and you're going to see. So now I have a ratio between volume 1 and volume 2 of the acid and the base. And watch out here, the ammonia is the base, so that's on top. So that's one equation which gives me a ratio between volume and volume. I can use another equation which says V1 plus V2 is 1 liter, because of course I'm preparing a buffer which happens to be a 1 liter buffer. Solve, these are two equations and two unknowns. So let's say in here, instead of V2, okay, or instead of V1, I put 2.51 V2, solve for V2, and then get the V1 and V2, okay? Not that difficult to do, and these volumes are in liters, okay? We kept these volumes in liters. So we found volume 2 and volume 1. So indeed, of ammonia, I need 715 milliliters of ammonia and 285 milliliters of the ammonium, both of which are 0.1 molar. Finally, you can get the concentration, but once you have the number of moles and the volume, you can just use that as number of moles. But get the concentrations of the acid and the base, substitute it into Henderson, and check. Of course, that wasn't the question. You already got the volumes, but check, indeed, if I use these concentrations, do I get a buffer pH of 9.6? And if you do, that means that the volumes that you have calculated are correct. Okay, so that's a nice check for you at the end. Quite a nice question. Okay, number 48, I'm gonna keep for my, for my next recording. So until now, we've looked at mixing of an acid and a base in certain amounts such that we get formation of a buffer.